So I could either do a quiz this Wednesday, but it would just be 15-7, 15-8. Or I could do a quiz next Monday, and it would be 15-7 through 16-1, I think. What do you guys think?
Monday.
All right, so Monday? So it'll be 15-7 through 16-1? Okay, so let's make that thing. Monday quiz 15.7 through 16.1. 16.1 was the vector field stuff? Yes.
Do you know if we have Memorial Day off?
We do. Did I not put it down there on the homework sheet? I might not have. One of my classes actually put a test on that Monday. I was like, well, let's not do that. I don't want to be here. You don't want to be here? We won't be here. Yes.
We have 14.8 in the homework, and it's, I don't think we did it in class. It's,
I think it's extra credit.
Yeah, that one's that's one of the ones I made extra credit, yeah. Yep.
So for homework, we have three homeworks basically. 15-7, 15-8, and 16-1.
Yeah, I'd say right now you should be at least trying problems out for 15.8,
Yeah.
right? You should have already kind of looked at 15.7 at this point.
They all right.
Yeah? Yeah, like I said, 15.7 is stuff we've already done before, to be honest. They just,
Though it's just so many, I call them spaghetti. It's like you create this big ass, and you need to integrate through
and then when you integrate each one at a time, kind of like,
yeah.
then it kind of becomes
It's like you miss one thing and it just.
Hell yeah. That's the thing
That's
about triple integrals in spherical especially, you got so many variables to keep track of. One little mistake will compound pretty quickly.
Yep.
So that's why when I grade it, that's one reason why I don't do scantrons. If you ever have a math teacher that needs you to get a scantron, they're not really a math teacher.
What's a scantron?
I'm not sure what, huh?
What's a scantron?
You guys know what a scantron is?
Multiple choice.
What's a scantron?
Oh.
Yeah. It's the multiple guess. Multiple guess paper. Anyway, you don't want me to make a multiple choice test. Let me just say it like that. Because mine would suck. Okay. Huh? Yeah, I have very interesting ways to make multiple choice actually measure what you know instead of can you game a multiple choice test. Any questions about that? Monday's quiz? We just in case you also don't know this, there is no test for it. So we're gonna
Only final exam?
yeah, the only test we have left is the final exam. We have this quiz, and I'm going to try to sneak one more quiz in there. We'll see if I can. We'll talk more about that probably Wednesday. I need to get you a slightly updated homework sheet and an updated grade sheet, so we'll see if future Jeff can do that. Yeah, because past Jeff, he doesn't get anything done, that guy. But maybe future Jeff, we'll see. So anything from any of that? Or anything from homework stuff for you guys working on? Any questions? Okay. I am an optimistic fool, so I will take that as a good thing. Yes? I don't know. I think I got up through, if you're on Cengage, you web assign? I don't remember how far I got up through. 16.1?
Yeah.
Okay. So real quick, if you're not okay with this, too bad. But if you are on Cengage, look at me. Oh, Nat?
Yeah.
There's one thing. I think that's all we got. Yeah. Okay. Please remind me if you think about it. Yes? I don't think about WebAssign. I don't. I hate WebAssign. I hate it. But some of you guys get a lot out of it, so what the hell? I'll let you use it. You guys with me? So if you can please remind me. If you don't remind me, that doesn't mean you're not responsible for the homework. You still are. So you probably want to have access to it, so you should let me know. If I don't put 16.2, 16.3, the other ones up there, okay? I would think right now, though, the furthest anybody probably is just getting into 16.1. Is that true? Has anybody gotten to chapter 16 yet? Tried anything out from there? No? Okay. I appreciate the honesty. So, the vector field stuff, let me see. Should I give you this? Not yet. So like, here's an example of a little vector field I was playing around with that we're going to look at later today. I kind of changed it up a little bit. Something we're going to get into today is line integrals. And we sort of did a little bit with it last time. This is where I had you guys draw the Riemann sum rectangles on a piece of paper and then you curled it. Yes? Remember doing that? Okay. And so it literally is on one level just math 180 just compressed so it goes out into another dimension. Yes? We're going to work our way up into, for example, do you guys know what happens when a charge travels into into a magnetic field, for example?
Interacts with a magnetic field.
Sure. In what way?
It depends on the magnetic field. If it's positive, it goes away. If it's negative, it attracts.
So so it'll change the direction of motion. In fact, if it's a constant, like upward magnetic field, it depends on the right-hand rule, but it's going to start to rotate. Yes. So we're going to be doing stuff like, if there's a field setup, maybe these little arrows represent the wind. And what I want to do then is, let me see, do I want to get into this? I'm starting to get into my little example. I don't know if I want to get there yet. Yeah, sure. Let's do it this way. I like it. What I want to be able to do is, depending on the path I take through the wind, how much is the wind pushing against me and how much is the wind helping me? Does that make sense? So obviously, if I'm going down into the wind, has anybody ever been to Chicago? Anybody? You've been to Chicago? You've been to Chicago. And of course, what is Chicago known as? I was not ready for how accurate that damn phrase is. Because I was trying to go on a train, I was trying to visit a friend of mine in Seattle. I was starting in Virginia Beach. And there was a derailed train in front of us, so they had to let us out in Chicago for a day. And I was like waiting to get a plane so I could fly out there. So I'm walking around Chicago, I step out and I'm like, okay. So you had to, so I always joke that if you're Chicagoan, you kind of naturally develop this lean to how you walk. I almost got blown out into the street. I mean, that was insane. So if I had to go to that building over there and the wind is coming this way, obviously the wind is working against me, yes? And then when I go back home, I'm like, yeah. Yes? So the path you take through such a field would determine how much force is going with you or against you. Do you agree with that? So if I have a set field of wind vectors are just coming right at me, if I go this way, is the wind helping or hurting? Neither. Now you could say it's kind of like pushing you off your path, but it's not directly helping or directly hurting you, correct? Now if I am going with it, it's helping. If I'm going against it, it's hurting. If I'm going at an angle, then part of my motion is being affected and part isn't, correct? Okay, I love it. So we're going to develop these line integrals. And one application is the experience something has in a field. What is it like? This is a specific type of vector field that I'm going to play with later, which is why I have these closed loops. So we'll come back to that a little bit later. First, I'm trying desperately, as I'm talking, to remember how far I made it.
We got the length of the plane, next slide.
Yeah, so let's do this. Yeah, the length of a curve. All right, let me just remind everybody. The length of a curve. Oh my God, Jeff. In the XY plane. And this is something I'm actually doing right now with my Math 280 class. So this is in section 10.2, which is the Math 280 topic. I think I told you guys that did I tell you I busted out the Etch-a-Sketch to talk about parametric stuff? Okay. Because then I can be the t variable and I'm controlling the x and the y, those knobs. Okay. So the length of a curve in the xy plane is given by this integral. Let's see, how do I want to write this? Sure, I'll write it out more explicitly. Now, if you, how do I say this? If you were to bring that dt in, you'd have to square root and square it so that it's able to go into the radical. And it would kind of cancel with each of these. And then it becomes a little more, it becomes a lot less calculus sound. So what I mean by that is, if I square root this and square it, can't I bring it inside now? Because now they both have the same root, so I can multiply the insides. And won't that just cancel with these dt's down here? So then I get something very, very strange. With no d anything outside, yes? Which is why we normally don't write it like this. But this is just, if I take the x motion and the y motion of this curve, and I take all of them, so the x and the y motion, the x motion dx squared plus dy squared, gives me how much I moved along the curve. Yes? So if I add those all up, I'll end up with how long the damn curve is. So this just makes sense. So if I have a curve, why? And I take every little dx, dy. So if I blow that up, I've got a little right triangle, and I know it's a right triangle because dx, dy means it's infinitesimally small, which means since this curve is smooth, which is one of the requirements, that's basically a straight line connecting them, because dx, dy means I'm on the scale that assumes so far in that since it's continuous and smooth, it's going to be straight line, locally linear, yes? And so it kicks ass. So then along the triangle, how far have I gone if the hypotenuse is my actual path? The square root of dx squared plus dy squared, yes. And if I add all those up along the whole path, I get the freaking length of the curve. Woohoo! Okay. Sort of like, and so what I want you to realize is, I think this is basically where I left off, I think. There's a 1 in here right now. There's a 1 in there. Because there's a 1 everywhere there isn't something in front of something, there's a 1, yes? This is equivalent to doing a double integral with a 1 in it, and that would give me an area, correct? You guys with me? Gives me a volume, but height 1, so it's effectively the area. So here's what I can do. Let's see, I've gotten a little ahead of myself? No. Okay, good. Yeah. Oh yeah, that's where I did that. Okay. If I want to integrate, so here's effectively what, let me write it like this. Here's what this really is. I'm going to write this all over again. Why not? Because nobody can get enough of my writing. That is the integral I just wrote, yes? And that I can represent using this notation. So this notation here just means the integral along the curve over the course of its arc length. So that's the little ds element. So the ds element ends up being this. Let me stop for a minute. And if you think about it, if I call the direction of motion the S standardly means the arc length, so the motion across the curve. So S is that kind of like piece of the curve, sort of like arc length of a circle is a piece of the curve. So now I'm just extending that idea to general curves. Doesn't have to be a circle. What is this? Well, that's going to be all this mess, but I can just call it ds. So ds is equal to the square root of blah, 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 blah. Okay. Let me stop for a minute. So this is the part that I normally can't handle directly. We normally rewrite this in terms of t because I can parameterize stuff relatively easily. It's just hard to get a hold of S, because why? It's an axis that's constantly turning. Yes? X, beautiful. Y, beautiful. S, what the shit are you doing, S? Because S follows the curve, yes? Does that make any sense?
So the point of bringing the dt in was just to illustrate that like this is just a hypotenuse, right? Like the dx squared plus dy squared.
Oh, if I parameterize this,
Right.
then it gives me something I can actually work with. If I don't parameterize it, it's really extra hard to work with directly. So it's a choice we make, but the choice only makes sense because otherwise it's really almost insane to try to do. Yeah. And it's because that S-axis, you can think of it as an axis, is just always following the curve, which is insane. Okay, I don't know. You guys are like, yep. Everything's insane in this class, Jeff. I know. Okay. Let me see. I'm trying to figure out which direction I want to go with this. Sure. So just to really hammer this whole thing home, let me say this part first. If S of t is the length of C between, so here I have a curve C, yes? A to B, this is curve C. So if I consider this to be the origin, this would be R of A, and this would be R of B. So if S of t is the length of this curve C between R of A and R of B, then this is stuff we've actually done before, but I don't blame you if you forgot. Just to really make this stuff more formalized. ds dt equals the magnitude of r prime. That's something we talked about way back when. Magnitude of r prime is of course that. R prime, well, what's r of t? It would be x of t comma y of t, yes? In 2 dimensions. You know we're going to go to 3. But in 2 dimensions, here, let me write this down. Just to remind you guys. R of t is x of t, y of t. Is that cool? So it could be like sine t comma cosine t. We've done this kind of thing before. We've looked at it. I've graphed it for you, yes?
Can I clarify what's dt represents?
As the parameter value changes. How does my arc length change, for example?
So is it? I mean, ds by dt sounds like a speed velocity kind of thing.
With respect to parameter change,
Yeah.
yes. So there's a lot of things we've done in the past where, with respect to arc length change, was difficult, just like I said now. But if I parameterize everything, with respect to parameter change, is easier.
Mm-hmm.
Not easy, but easier. Because ds again is this trippy thing.
Because we don't want to do dx dy, so that's why we.
No, we totally do. But we want x and y in terms of t.
Mm-hmm.
And then I can do this derivative really easy. Okay, let me stop for a minute. We've done that ds dt is r prime. If r of t is x of t, y of t, what's r prime of t? I don't know why you became an F.
It's ds dt x component of s.
dx dt, dy dt, yes? And what's the length of r prime? Yes? Which is that? Okay. Can we stop for a minute? Okay, so what's trippy about this, in Math 180, we're restricted to motion along the x-axis, so I have just dx. Then we saw how double integrals and triple integrals in 2 and 3 dimensions involve, the order's got to be careful, but okay. So you got dx, dy, dz. Now, our path is being determined by this curve. So if I parameterize the curve, so I know at time t I'm here, at time t I'm here, at time t I'm here, blah, 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 blah. Then I can write kind of like my motion is captured by this now. So in Math 180, my motion is captured by dx. And when we start doing double integrals, triple integrals, my motion across a region is determined by kind of like my choices, right? But it's also dx and y z, or change the order, or already theta if I'm doing polar, blah, blah, blah. So now my motion along some predetermined curve has to be based on how it kind of moves, and that's what this is. So this sucker right here. So real quick, I really want this analogy to hit home. Is everybody relatively okay with it? If I start here, you can't help but get there, yes? Just this piece by itself. That's r of t. That's r prime of t. That's the length of r prime of t. Kabam. This is kind of a measurement of how quickly this is moving. This curve is moving. It's keeping track of how it's moving and how quickly it's moving. Shoot, I forgot where I was going to go next. Let me see. Okay. That's relatively quick. As I get older, that pause is going to be longer. It's going to be fun. I forgot what I was going to do next. Give me about 5 minutes. Okay. I love you guys. You're all like, you're there, man. Shut up. If I double integrate across a region, dx, dy, that gives me an area. Because the inside is 1. Yes? If I, this keeps track of how things are changing, how I'm scanning this region. Now I don't have a region, I have this curve to kind of like move along, and that's what this guy captures. So the same way that when there's a 1 inside, I just end up with area, when there's a 1 inside of this, oh boy, it's really fun writing this over and over. There we go. When there's a 1 inside of this gives me length. Length of C. If I put something else in there, then it becomes that idea of the curtain, right? Where the height kind of changes potentially. So I'm capturing that area as I move along that snaking path, that C path. The square root business, that whole thing is kind of like dx dy. It's just there. It's just a part of what needs to be there. It's sort of like rho squared sine phi in spherical. Yes? Where the shit did that come from? It's just got to be there to make that whole thing make sense. Now just a real quick word. It's unfortunate that 15.9 isn't really part of the curriculum for some reason, and we wouldn't have had time for it even if it was. But there's an idea called the Jacobian. And the Jacobian kicks so much ass. Anybody in my linear, I think I referenced it real quick not too long ago. Jacobian is kind of like this matrix, and you can figure out the determinant, and if you shove in there the coordinates you're kind of using, it'll spit out what's supposed to go at the end of your interval. So remember what I told you, how many coordinate systems exist? I think I told you there's 50 or so that I've actually worked with directly. There's maybe 7 of them that are like the fundamental ones, and then you kind of mess with them a little bit to make different versions of them. In each of those cases, if I just use the Jacobian, I know it's just supposed to be RD theta, it's supposed to be rho sine phi, blah, blah, blah. If I just use that matrix, it'll tell me what's supposed to go at the end. Okay, all of that was a side note. All of this at the end is a part of the integral. You with me? I think at this point everybody's cool with the R in R, dr, d theta. It just is a part of that thing at the end. It's just a part of it. And then whatever I put inside of it is determining what I'm finding the interval. If I put a 1 in there, I'm getting some kind of an area. Yes? So it's the same exact thing that's happening here. Okay. Maybe. So you'll see sometimes they'll call this a weight. To me, that never really made full sense. But it literally is kind of like, this part is just telling me how I'm moving, so it has to be there. Sort of like in 180, if I didn't put a dx, the interval wouldn't make any sense. Which direction am I going, Jeff? Is it dy, dx? So this whole thing has to be there. All right, I think I've beaten that to death. Okay, I just really wanted to make sense. Now we'll go back to this one, yes. So in general, if I want to find the area of a curtain, right? Sort of like when we curled our papers up that you guys drew the Riemann's rectangles on. If I want to find the area of that curtain as it kind of like sways around and moves around, follows the C path, that's the integral I would have to evaluate. Have you seen this integral before, the little C on the bottom? Did I put that up here before? So all this means, the way to read this is the integral of f along C. And C's got it, they have to tell you, is C a straight line in the xy plane? Is it a circle? Is it whatever? Are you guys kind of with me? So part of what we're going to do later today is just get practice in how to write various curves, how to parameterize them. That's going to be the first part of a lot of problems. Okay, you guys look appropriately excited for that. Okay, you look like this. What the shit? Okay, I understand. It does suck that the hardest stuff always comes at the end for every class. And you're like, oh, good, this is lining up perfectly. All right. So let me write this in the way that's most generally useful. Jeff. Let me start over here. So this means my f has been parameterized. Then I've got to replace ds with what it is in terms of my parameterized business. Chumba Wumba. Yeah, it is. Okay. Okay. That looks a little bit daunting. So let me see. Let's try an example out. Here, this is beautiful. Okay, this is a nice little quick example. Do you guys want a concrete example? I'm joking. Of course you do. If you didn't, I'll be like, holy shit, you guys are weird. You guys are as weird as I am. So let me give us a deceptively little tiny problem to figure out. Look at that. That looks very harmless. It's not going to be terrible, but it's yeah. Where C is the arc. Oh yeah, let's do this. This gets really interesting. Okay, I might as well do this. Where C is broken into two curves. C1 is the arc of y equals x squared from 0, 0 to 1, 1. C2 is the line segment from 1, 1 to 1, 2. So trying to be a 1 and it's trying to be a parenthesis. By the way, you can see why I want you guys to do homework in pencil. Okay, so real quick. Could you guys do a quick little sketch of the path we're taking? Just do a quick little sketch of the path we're taking. It's nowhere near as difficult as you might get. It's just 1. Y equals x squared from 0, 0 to 1, 1. And then the line segment from 1, 1 to 1, 2. That should take you roughly 17 seconds. So from 0, 0 to 1, 1, it's following this parabola. And then from 1, 1 to 1, 2, it's following a straight line. Okay, deceptively simple. That is the xy plane, correct? Where is everything happening though? Yeah, in this case above it. I like how you stopped and thought, because since it's 2x and we're in the first quadrant, it will be above it. Of course, at the origin, it's hitting. But then the minute I start taking it off, so let's see if I can make this. Let's say that, what's going to make the most sense? Let's say there is a tent that has collapsed. You ever been in like a really big tent, and like somebody starts to take it down, and one part of it just drops to the ground? So I'm on the ground, and I'm like, oh shit, the tent's like on my head. Yes? That's me here. Yes? And they start to crawl away from it. Now the tent is down on the ground in that one spot, but then it goes up because there's another pole over here. Are you with me? So the tent kind of like is, for some reason, the height is perfectly twice the x position where I am. So if I crawl along this parabolic arch, what's the height of the tent doing? As I crawl along here, those of you at home, what's the height of the tent? What's the height here?
10.
What's the height here?
1.
2. Is everybody with me? You guys with me? Everything is happening above or below, depending on what the thing is, yes? If I was in this quadrant, then I would have been below. Okay. You guys see what's happening? So, and then of course, what's happening from here to here? What's true about the height from here to here? Constant, kick ass. So I get to a point where there's 2 poles maybe set up, and then the height of the tent is constant. Yes? Okay, maybe. Maybe? I do default to tents for Math 281 very often, because tops of tents can be very differently shaped depending on where you put the poles and how tall the poles are. You guys are all with me? So it kind of makes sense that I got all these funky ass shapes that are above the ground of the tent, which is the XY plane. So the very first thing we need to do is to parameterize the 2 curves. So I am going to have 2 integrals, because at the point here, everything kind of changes. So I need 2 different intervals. How do I do that? Look at C1. I want to parameterize C1. Do you guys remember what it means to parameterize something? Yes, so I could say, and ain't no freaking reason I need to. I could say let x equal sine t. And then what would y be? Sine squared t, yes. And then I have to figure out what makes it go between these 2. Are you guys at all with me? So like, okay, I'm not going to do it. Don't even write this down. Why am I even saying this? I could say x equals sine t. That would mean y is sine squared t, yes? When t is 0, what point am I at? 0, 0. So see how it matches up? So t is 0. When do I make it 1, 1? How do I get these to be 1 each? If t is, you can do it. Pi over 2. You can see what I'm saying. I need you to understand a couple things. Do you guys want to do this? Because then you have to throw that shit into your function, makes it a little bit worse. I don't have to choose x to be sine t, but I could, and that choice leads to what y is, which leads to what t has to be to actually go between the freaking points they told me to. Are you guys with? If I would have chosen cosine, things would have been screwy, because t couldn't start at 0 then, because then my x wouldn't have been 0, it would have been 1. You guys with me? So then I would have had to adjust it. Holy shit. Okay, I'm gonna love you guys. Stay with me, please. So I'm not gonna do that stupid shit. What is the most basic thing you try to do when you want to parameterize something? Just let the variable that represents the input, just let it be t. Okay. All right. So this is insane, Jeff. Okay. When am I going to want to do stuff like this? If I'm dealing with what kind of a curve? Circular. Then this is going to kick ass. This is going to be the best thing in the world. This is not circular. That's maybe not the best way to go. Would it work if I did that way? Hell yeah. I'm not going to do it that way. So, if I look at C1, x is t, so y is what? T squared. And what's t go from to? 0 to 1. 0 makes it 0, 0. 1 makes it 1, 1. Can you guys figure out a parameterization for T2? It's its total, its own thing. Yes, it doesn't have to have a damn thing to do with our choices for C1. It's going to be a separate interval. Figure out a parameterization for C2. If you're not sure how to do it, we'll do it together in a minute. This one's kind of silly. What stays constant? So if x, what are you going to let x equal? 1. And then what's y? T. Y can't be 2. What does y stay constant? No. Y goes from 1 to 2, correct? So if y is t, does x change? Will x be dependent on t then, because t inherently changes? If x doesn't change, I can't make it dependent on t, because then it would change, and that's a contradiction. Is y changing? Shit. So I can make it dependent on t, because t inherently changes.
We don't care about the fact that it starts not from 0 but from 1.
No, we don't care, because what are my limits going to be on t? That's what I can choose.
Uh,
Now, if you want to force the limits to be something else, then you do have to change what this is. But what I normally do is I set this up and then I figure out next step, what's my t limits have to be. So what very obviously do my t limits have to be?
1, 2, 3.
That's from 1 to what now?
2.
To 2, because that's where I want to stop. Cool. And so, really quickly, just because I just thought of this, why not? Just suffer with me for a minute, sorry. Let's see if this works the way I want it to. So this is in parametric mode, yes? If I go to y equals and I put in here, oh yeah, it's right. I forget how to do that in this calculator. I'm not going to try to do it, damn it. What I forgot is how to control what t is for 2 different functions of t. I know how to control what t is for everything. I'll let it go. Very sorry. But if you were to plug these into the calculator, it would create these pictures. Yes? Okay. So what does this mean? What can I do now? So now I can translate to this. Now A and B, I can't remember if I was specific about this, but A and B are just what t is doing because that's what it's based on, yes? So I'm going to make 2 integrals, one for C1, one for C2. So let me just kind of do this way. Okay, that's supposed to be an integral sign, but it got smushed. So really quick, ds, how do I figure out what ds is? Yes, so let's see. So let me remind us. For C1, x is t, y is t squared. What's dx dt? 1. And what's dy dt? 2t. So what is the square root of dx squared, dx dt squared plus dy dt squared? Yeah, 1 plus 4t squared. Cool. All right, let me stop for a minute. Now, nothing we've done is like exceptionally difficult, but there's a lot of it, and the problem looks so damn tiny. So why does it make sense that there's going to be a decent amount of work? because we're following these weird-ass curves. I'm not just scanning a region, which is very direct. I have to follow this damn curve, which takes a bit of work to make my math realize, hey, math, we're supposed to be following this curve. So what's my integral going to look like for C1 now? T was going from 0 to 1. So 0 to 1. 2x, but what was x? T. Times ds, which is the square root of blah, 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 dt, yes? Mm-hmm. So that would be all this business here. Now considering, do you feel like you're on the right track when you see that? Yeah. What is it about that that tells you you almost are definitely on the right track? U-sub. It's a U-sub, yeah. Could I make a problem where you have to do like partials? Yeah, but I'm not going to do that very often. Very often. There it is. I'm going to do it very rarely. So, I mean, you can kind of tell if you're in the right direction if it becomes something like U-sub maybe. Yeah. Okay. So that's what happens as it moves along here. And let's see. Go ahead and integrate that. This it? Yes.
Where did we get this integral? I'm gonna find it. Like the template for this.
Okay. So this is f here, right? This is f of xy, and this is ds. Okay. Yeah. Now I changed it into f of x of t, y of t, and this is what ds becomes. Mm-hmm. Yes. That's it. That's it. So 2x. What's x is a function of t?
I see.
T. And then ds becomes this thing here.
Why 2x?
Because that was the problem from the very beginning.
Oh.
Yeah. So instead of 1 inside, I'm not just getting a length, I'm getting an area of the curtain. Yeah. So let's see, what you should end up with. Oh yeah, you should end up with something kind of gross. You should have, I think, 1/6 u to the 3/2 from 1 to 5.
Yep.
So u is 1 plus 4t squared, du is 8t. You need to put a 1/4 out front to make it become 8 inside. Then you get the square root of u, blah, blah, blah. You guys want to see all those steps? I can. Yes? Okay, I'm with you. Get out of here, you silly. Got to show the steps. So u is 1 plus 4t squared, du is 8t dt. So therefore, I need a 1/4 out front so I can make 8t inside. Is that cool? So now this is du. This will be the square root of u. My limits will become, right now they're still 0 to 1, but now they're going to become, when t is 0, u is 1. When t is 1, u is 5. Okay. This is relatively easy compared to some of the other stuff we've done this semester, but it's not easy. I just want to let you know. So this will be 1/4 times, this will be u to the 3/2, so then I multiply by the reciprocal from 1 to 5, which is 1/6 u to the 3/2 from 1 to 5. Which is, whatever, that's just gross shit, yes? It'll be, so this much will be 1/6 5 to the 3/2 minus 1/6, okay? But we still haven't done the other path, yes, okay. Sorry. So just to remind you guys, C2, we said x was 1, y is t. T goes from 1 to 2. And what is the square root of, what is dx dt? This is nice, 0. And what's dy dt? 1. Yeah, so the square root of 0 squared plus 1 squared is 1. That kicks so much ass. So ds just becomes 1 dt. Is everybody understanding? Yeah, so this would be the square root of 0 squared plus 1 squared is 1 dt. Okay, so this becomes integral from what to what? 1 to 2. 2x. And what's x? X is 1, so this is 2 times dt. Now, what if I would have really been smart, I should have said, you do this one, I'll do this one. But sounds like more like what I normally say. I'll do half. So what does this become? 2. True, but 2t from 1 to 2. That'll be 4 minus 2 is 2. So then your end result is 1/6, 5 to the 3 halves, minus 1/6 plus 2, which is 11/6. Which, you know, I know you guys knew that was what it's going to be from the beginning. No, you don't know. No. The unfortunate thing about these problems is, since everything is happening above or below the picture I normally draw for myself, it's really, really hard to tell if your answer makes physical sense. One thing that does make physical sense for sure is this answer is positive. Because my function only had positive outputs along the curve I was looking at. Yes? Okay. Can somebody tell me, what do you guys think if I were to add this onto my, basically the inverse of that?
It would be 0.
Why?
Because we would have the same positive and a negative.
Yes, because all of these along here, it would be up here, and then it goes to 0, and then it will go underneath along here. So all the positive parts of the area would be negated by the part that goes underneath. Okay, I love it. I love it. Okay. So that I love that problem because it's for one thing, it kind of shows you, and I hope you don't get too freaked out about that, how a problem like this can kind of blow up. And it has to, because this is being really deceptive. There's a lot to this just by itself. And in the process of putting this into a better way, these change. And then this kind of determines what is going to happen with those. So there's a bit of a dominoes. Once I make a decision here, that affects this. Could we have set up the parameterization differently? Hell yeah. Thank God we didn't do sine t. Yes? That would have sucked, yeah.
Everything else makes sense. Why in C1 is x equal to t? Is that just how we decided to parameterize it?
Oh, okay. I'm working with y equals x squared.
Right.
Unless something exceptionally weird happens, I almost always will just make the input variable become t. Because then I already have a relationship between y and it, so I automatically have a relationship between y and t. Does that make sense? So if I would have followed y equals sine x, I would have made x t, and y would be sine t. With that said, I really want you to understand, we're not going to get so into this, obviously, because how much time we have left in the semester, but some of you guys might realize there could be situations where your choice of how to parameterize the curve you're following could totally change how difficult the resulting problem is. Here's an example where I could have just purposefully chosen this horrible thing that would have made this really horrendous. You guys understand if I would have, dx dt would have been cosine, that would have been inside the radical, no, no, thank you. But there are other cases where you don't want to take the most obvious route. You actually want to pick a different parameterization because it makes better things happen in your interval. You guys see that? The choice of how to parameterize your curve is huge. For most of the problems we're going to look at, it's going to be basically the obvious choice you want to take. But if you ever go deeper into any of this, depending on what track you take after this in mathematics, it could become a big part of your whole purpose is to what is the best curve for a given, what's the best parameterization for a curve for a given problem. Does that make sense? Yeah.
We do a little like 5-10 minute break.
Sure. Yeah. It's not a bad place. Yeah.
Actually, the work that you did first.
My work. Oh wait, over here?
Yeah.
Sorry guys. Where do you want it? Here? I'm not sure which part you want. So take, let's do a 5, we'll come back at 1:35. We'll compromise. Turn this guy off. All right, guys, so I want to point something out. Let's see. Is everybody back? No. It's a strange thing. It looks like the rapture happened, and appropriately enough, I'm still here. You guys are still here too, so we'll go see whose car is available. If I have, for example, this region here, because we're about to do something that might, well, this phrase doesn't have the same impact as everything seems to. We're about to do something that should seem a little weird, even relative to what we were just talking about. We're about to look at something like this.
This is still 1602.
Yes. Now, real quick, if I want to integrate the curve, oh yeah, let's say f is 1. Is that cool? F is 1. So if I integrate f ds, let me see if you guys can get this. Just gonna leave that up there. You guys try to figure it out. I just want you to figure out integral f ds across that curve. Don't say anything. I'll ask you one question that will help you along your way. Since f is 1, what should the integral end up representing? The length. Okay, so do it. Don't rewrite ds. Don't do any of that shit. Just write down the answer. This is sort of like in Math 180 when you first learn integration. And then they give you a graph of the triangle, and they're like, find the integral. Let's just find the stupid area of the triangle, right? So you don't have to do any calculus. You with me? Because since integration represents area, if there's an easier way to get the area, shit, yes, I'm going to do that shit. So if that integral represents the length of that curve, what's the length of the curve? Go ahead and tell it. Who's got it? How'd you get that? 2 pi r, yeah. So, and this is pi over 2, this is half of it, right? So this would be half of 2 pi. Because the whole circle would have a circumference of 2 pi, so this would be pi. Okay, let me stop for a minute. Is everybody with me? If I do integral curve f dx, that will only consider motion in the x direction. And I should have, this is kind of like my fault, but let me put these on here. I'm going this way, yes? That's what I kind of like inherently mean. I'm going that way. You'll see why later that's kind of like the default, is to think it's going that way. It's kind of like the convention. All right, let me see if you guys are cool with this. As I move along that path, I'm only considering the x motion. Does anyone have a guess as to what that would be then? Close. Don't overthink it. And you're all like, I don't know how to correctly think it. This will be -2. Because where did x start? 1. Where did it end? -1. So it is literally the length I move just considering the x direction. So this is like, if somebody's doing this along this bridge, yes, I'm thinking about this bridge in Australia. Say you walk across the bridge like this, you know, you got the bridge this way where people normally go. Let's say you're crazy and you're walking across the actual, what do you call it, suspension part, right? You're walking, somebody above you looking down will see you only moving like this, yes? That's all they will see. So if you start at positive 1 and end at negative 1, according to them, how far did you go? Negative 2. What about the other one? Yes. That would be somebody, no, I'm not 1, it's 0, sorry. I don't know why I said yes when you said 0. That's somebody looking from this side. As you're going up and down, so from their perspective, you just do this. Yeah? Yeah. How far did you go? 0. Is it you guys with me? It's sort of like in Math 180, the difference between total distance traveled and displacement. Yes? Displacement. Yes? Yes.
What is it? Why will it be dy if we don't take it? If we take the whole path? You know what I'm saying? I thought dy.
The whole path is being taken in each of those situations. Just what is being taken into consideration about the path is different. So if I'm on a hike, if it's a flat hike, I might rate that as 0. I'm only interested maybe, depending on how much cardio, whatever I'm working on how much my path goes up and down. Yes? So the entire path is being walked. If I walk completely flat land, I did not just walk 0. But in terms of vertical difference, 0. Now, if I am going up and down, let's just say I'm going up, then I've got a complete vertical change, yes? Now, if I also come back down, this process just takes away from what you gain. You gain, you lose, 0. Let me stop for a minute. Right now, we're about to kind of do a few examples of this. And what's funny is we kind of do it in preparation of what we're about to get into. Because we're about to get into is going to take a little bit more discussion, but it's going to lead to parts of an integral looking like these two. We're going to start with something like this, and it's going to lead to these two separate things. And there will be situations where the two will be equal. In this case, are the two equal? If I add those two integrals together, do I end up with what I got all the way? No, of course not. You guys kind of with me? Because what I'm operating in is not a certain type of what's called a vector field. So in this case, it's just 1 everywhere. Okay. So we're going to focus on, for just a bit, line integrals with respect to just x and y. So just to remind you guys, this would be integration with respect to the full arc. If I make it this, that's with respect to the parameterized version. Let me write it the shorthand way here real quick. If I make y prime 0, meaning I'm looking down from above at this guy going across the bridge. I'm making all my vertical displacements. From that perspective, physically, it looks like y prime is 0. Yes, but here I'm just going to force y prime to be 0. What happens? Huh? Yeah, you get a to b. F square root of this squared is just this. What is x prime? I should have written it all the way out. I knew it. dx dt times dt becomes dx. So if I ignore the contributions from the y direction motion, I pretend like there is no y motion. This sounds a little bit like partials, yes? Don't worry, this is not going to be a big, I'm not going to, this is partial integral, no, sort of is, but not really, because you'll see. Similar thing could happen if I make x prime 0. Exactly the same kind of thing. So let's try an example out. Yeah. C is the line segment from -5, -3 to 0, 2. By the way, a lot of this stuff is going to feel like it's really beyond your reach, but the more you do this, and I think once I give you my little handout, I'm going to focus on just finding C. That's going to be a huge part of the problem. It's going to be just represent C. The minute you get that figured out, everything else just flows from that. So the harder that is to get, the harder the whole problem is. And obviously, if they stick a worse function in there to worry about, that makes it harder. But can you guys parameterize that? There's something the book considers a shortcut. Do I even want to show it to you? I always forget it because I don't like doing it that way. Sorry guys, let me see if I can find it. It's something we knew way back when we were first started doing space curves. Why do I always forget this? Because you never use it, John. Oh yeah, that's right. Oh, there it is. Perfect. That little tiny thing. Stuff look familiar to anybody? So trying to parameterize a line segment, you could do this. If you want to. Personally, I wouldn't. I just don't. That's why I forgot about that stuff. So who was able to work on this while I kept talking? Has anybody got this? Oh, okay, sure, yeah. One way to do this is to figure out just the xy function, right? So you got what again?
Y equals x plus 2.
So y equals x plus 2. That works because plus 2, kick ass. So then you can let x equal t, and then y equals. Now, if you do it, become a plus. If you do it that way, you have to be careful about what t goes from to. Let me write this a little better, sorry. X is t, y is t plus 2, because you decided to figure out the xy function that goes through those points. Kick ass. Can you figure out what t goes from to? That's not too bad. Because what is everything dependent on in the choice you make? X. So what does x go from to? Yeah. So in this case, that wasn't too bad. Sweet. Okay. If you can't or don't want to do that, well, we'll do it a different way in a second. Let's see what this leads to. How do I deal with? Now, your next question might be, how do I deal with this? But what's dy? No, yeah, dy is 1 d. Okay. Yes. Dy is dt. So this way is better, but it's not going to happen too often where I just have one direction that I'm worried about. When I am, that kicks so much ass. I can go straight off of this. I don't have to do the radical business because I don't have two directions of motion to consider. I'm ignoring one of them. In this case, I'm ignoring the x direction motion, yes? I love you guys. And then what's x again? T. And dy is dt. And what's it going from to? -5 to 0. And then what do you get? Yeah, you get t squared over 2 from -5 to 0. So you get negative 25 halves. Make sure I didn't leave anything out.
It's
Just
is it
25 on
no, because it's squared. You're subtracting.
Oh yeah, positive 25. I'm being silly. Okay, thank you. Oh no, it is negative.
You're subtracting.
I love you guys so much. So when you plug a 0 in, and then you subtract what you get when you put -5. So I agree with you that -5 squared is positive, but you're subtracting it because it was big ass f of b minus big ass f of a. I appreciate that. Okay, maybe. What did I do down here? I think I redid it for some. Yeah, I'm not going to do that. No, I'm not. I kind of play with that problem a little too much. Let's see. How about this? Let's do that same thing, but we're going to do it along the arc x equals 4 minus y squared. Well, what else do I want to say? Sure. From -5, -3 to 0, 2, that same path. That's not the same path, but it's the same beginning end points, but I'm taking a different path now. So, would you expect this, does everybody see that's the same exact interval, correct? Same exact interval, yes? From what we just did. You guys are still looking like, okay. So we just did this problem, and now we're doing this problem. Is that the same interval? Yes, it is. Is the path I'm taking different? Yes. Okay, same interval. Path I'm taking is different. Yes? Should I expect the same answer? No, hell no. So, if I have this, all right, beautiful. I have the ceiling. Look at the ceiling, everybody. So if I, yes, sir. -5, -3, yeah, I think so. I try to make it the same. Yeah, it was -5 to -3.
minus y squared.
0 to 2. Oh, that's a minus. Yeah, sorry. That is a negative that was in the sun too long. I'm sorry. Okay. So guys, if I want to go to you, I forgot your number. I'm sorry. Feel that. I'm sorry. If I just walk straight to you along the path, I'm going to get this area from my feet to the ceiling. Yes. If I change my path, now I'm going to get a lot more area, correct? How do I get to him to get the least area? I go straight to him. If I take a different path, even though I end up in the same place, it's going to depend on how long that other path was. And also, what the function is doing over that new path I'm taking. Does that make any sense? I really want this to make sense. Okay. I could go to him and it's negative. I got like this, and then over here it goes underneath. So when I go this way, it's a negative area. So it's path dependent. Now some of you guys might realize that kind of tugs the memory strings about like limits and paths to take. Don't forget, it's not going to be that. Okay. Just I take each problem as it comes. So then the question becomes: are there intervals where it doesn't matter what path I take? That was neat. Yeah.
It's not a question. It's not the answer to your question. I just want to ask why we're doing dy.
Oh, because that's the problem. That's the problem I was given. Yeah. Whoever is doing this just cares about the y motion. Yeah. Okay. Now, one situation where you might only care about the y motion is you're wondering how many things you're collecting over time, and the things are coming at you like this. You don't care about this motion. All you care about is this motion. How much people are getting through this gate or whatever, even though they're taking a serpentine approach. Okay. And again, just reminding us, there is a physical situation in which we will end up with these intervals more naturally. Right now, it's a little weird to come up with the situation that actually tells you why we're doing this by itself. So help me out. How am I going to parameterize this one? Yeah, let's try y equals t, then x equals 4 minus t squared. That's what I would try. Now you got to be careful because now you need it. This isn't too bad though. Whenever one of your variables is just t, that kicks whole much x. Y is t. Therefore, what does t go from to? Negative 3 to 2. Say again?
It also means dy equals dt. In this case, doesn't it?
Yeah, let's see. So dy is dt, totally, which is cool.
That's why we set up the problem that way, right? Like you look at the problem and you're like, I'm setting y equal to 2.
Oh, also because if I make x t, then I have to solve for y,
Yeah.
and that would desperately suck. Yeah.
Or just like since the dy is in there.
Oh,
Kinda clues
yeah.
you in.
You got competing interests. Would it really get so disgusting if I force this guy to be just dt? If it is, then I'm not going to do it. But it's a balancing act between the two. Okay. So how do I rewrite this now? See, negative 3 to 2. X is 4 minus t squared. Dt for dy. And then that's not that bad. Yeah? Not too bad. Oh yeah, where was that at? Shoot. What time is it? Okay, we have some time. Okay, good. And then, is this all right? I mean, this will be 4t minus 1/3 t cubed, and you shove negative 3 and 2 in there, and I think you get 25/3. Which is kind of neat, because what do we get for the other path? Yeah, negative 25 halves. Why did we get a negative here? Because my height is determined by my x, and for most of this path, my x is negative, correct? So I'm getting negative area. This path, my x, well, let's see. If I go, let me see if I can get you guys to be with me. If I graph this path out, 4 minus y squared from, oh God, negative 5, negative 3 to 0, 2. And 0 would be, wait a minute. Oh yeah, Jeff, you're so funny. 0 is, 0y gives me 2x, so that would look like this. This is a little bit trippy, but you're underneath for a bit, and then you're over for a bit, so it looks like I was over for a longer. If I got 25/3 right, I don't know if past Jeff got that right, hopefully. Maybe I did. Yeah, okay. All right, so it's not easy to tell ahead of time if your answer is going to be negative or positive, because you don't know how long the influence lasts. I mean, this looks like longer, but this ended up being a longer than this was.
It's supposed to cross at 4, so it really does look longer. You make it cross at 4.
4?
Yeah, because x equals 4 minus y squared.
Oh, when y is 2, yeah, when y is 2,
So y is
x is 0. When x is 2, oh, I see, yeah, I'm not thinking, this should go further, yeah, okay. So if I graph this a little bit better, then you'd see it was longer on the x positive side. Okay. Yeah, I'm not worried about that one. No. Interesting, Jeff. Okay. So now I've got line integrals in space. I'm pretty sure this is still 16.2. Let me see. Yeah, because 16.3 is the analog to the fundamental theorem of calculus for line integration. So all this does, this is just one little piece of section 16.2. This just extends everything we've been talking about to 3 dimensions. So you get f of x, y, z. That leads to f of x of t, y of t, z of t, yes. Square root of x prime squared, y prime squared, z prime squared. Yes, everything just throw a z on top, yes? Just like Pythagorean theorem grows for an extra dimension, all these things just grow for another dimension. So you're going to have very similar problems, just with one more dimension to worry about. Something we're fundamentally used to in this class. That's the tagline of this class is Math 180, now in one more dimension. So, oh yeah, let's try an example out of the book real quick. What did I say? Page 1137. Yeah, okay. I don't know if you guys remember, that back in the day we actually graphed a few of these. These line curves, space curves, yeah. So this is kind of like I have a, yeah, sure. I have a radiation field in the room, yes? Quality. That's that. Right? And plus, trying to figure out which way to navigate, and I'm going up and down, there's stairs and so forth, but the radiation is less in some places, more in another, and I know the equation of the radiation field in this room. So I'm trying to figure out, this is the path I must take, because there are, radioactive beasts and monsters and fire and whatever. So I'm like, how much radiation am I going to take if I go along this path? So I can integrate through the field and see what's the total accumulation of radiation along this path. So it's just a 3-dimensional analog to what we've been doing. So let's see. This problem says, integrate this function. Where'd you go? There you are. Where C is the circular helix given by, now this is really nice. Now, some of you guys are like, oh, come on, what the shit. The beautiful thing is, I need you to understand, these problems, I don't care if I give you 2 dimensions, 3 dimensions, 78 dimensions, when you parameterize the stuff, it all becomes a function of one variable, t. So they all kind of filter down to being kind of Math 180. Now, there's some work before we get there, but I know that's going to happen. What's it given by, Jeff? X equals cosine t, y equals sine t, and z equals t. Just because. And we go from 0 to 2 pi because we are traditionalists. So what do you think you start with? You could notice a couple things. Like the integral is going to be easy to rewrite because I know what y is exactly, I know what z is exactly. ds, what's involved in ds? Square root of x prime squared plus y, so I got to figure out what x prime, y prime, z prime is, yes? So what's x prime? Negative sine t, what's y prime? Understanding this is with respect to t, yes? So I don't have to write a bunch of stuff. Cosine t. What's z prime? 1, kick ass. So then what's the square root of all that business?
Sine squared plus
Yeah, sine squared plus cosine squared is
1
plus 1 squared, 2. So ds is this dt. That's almost too nice to believe. So circular motion, it's awesome if we parameterize it with cosine and sine. So anytime you see circular motion and you have to choose how to parameterize it, dear God, cosine and sine. The earlier one was parabolic, so we didn't want to use that. So now I can just rewrite this. So t is going from 0 to 2 pi. Y is sine t. And what's z? T. So I get sine squared t. Is that cool? And ds is rad 2 dt. And as I promised, that's an example interval that requires you to use a trig substitution, right? You gotta use that. Sometimes you call it power reduction. I just call it a reformulation of the half angle formula. You guys at all with me? How do I do that? Yeah. So let's see. Rad 2, 0 to 2 pi. 1/2.
Minus cosine 2 theta.
So let's see. Cosine 2 theta is equal to 1 minus 2 sine squared theta. So if you solve for sine squared, you'll get 1 minus cosine 2 theta over 2. So it'll be cosine 2 theta over 2. But what I normally do is I just pull the 1/2 out. Oops, theta. T. Pull the 1/2 out, and I just get 1 minus cosine 2t. Can I stop for a minute? Depending on how long ago you took Math 280, this is a big deal in Chapter 7. Math 280 was the sine squared and cosine squared. And then when you integrate this, what do you get? So you know it's not this, right? You got to kill the 2 that wants to come out when you differentiate it, yes? I love you guys. So, integral e to the ax, it wants to be itself. If you take the derivative of this, I'd have an a. I don't have an a, so I must add an over a to kill it. Same idea happens here. Can't be just sine 2t, because then a 2 wants to come out. There is no 2, let me kill it. And that goes from 0 to 2 pi. So you get rad 2 over 2 times 2 pi minus 0. And then when you plug a 0 in, you get 0. So you get, what do you get, Jeff? Pi rad 2, I believe. Yes. Sorry. Yes. Yes.
What did you get ds? 1 over square root of 2.
Where are we at? Sorry?
1 over square root of 2.
Oh, no. This is z prime is 1.
Oh.
So then ds would be each of these squared added under square root. Yes, okay. Okay, I like it. You would, Jeff. So, like I said, very often one of the hardest steps, and not even that hard really, but it's going to be how to parameterize the curve you're given. Okay. How hard do you want to make it, Jeff? Ooh, I got time. Okay. I get to a certain point, I can give you a certain handout. Let's see, blah, 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 blah. All right, let's do this. So in an earlier section, we found out, or we would have found out, that work is force dotted with distance. Really weird thing about work in physics is if you pick a box up and then you put it back down, 0 work has been done on that box.
If it stays up.
Yeah, if it stays up, I've done work because I've actually lifted it against a gravitational field. If I put it back down, then the gravitational field just brought it back down. So overall, I would have done no work. Now, if I do that over and over again, I would say, I feel like I'm doing work. But technically, the work done on the box would be 0. Does that mean we did not do any work? No. It's just that the work done on the box throughout that series of events would be 0. That's
Well, that moves the
if
vector field
I. Good.
Well, it moves the vector field out.
Do it again.
Never mind.
Sorry. Blah, blah, blah. So, if I have a... I love my little drawing here. Yeah, okay. So, if I have a field, so for example, I've got a little main, electric charge, and there's an electric field set up, and I want to push that electric charge through the field. I'm going to be doing work on the electron, more work, of course, if the field is trying to push it the other way. I'm going to be doing less work if the field actually wants to move that way. And of course, if I'm perpendicular to the direction of the field, then I'm actually not doing work either way. Yeah, this gets interesting. So if I want to extend this to a field, let me see if I can recreate this drawing worth anything. So I've got this force field. Let's say it's we can even think of it as just wind. Yes? So I've got this wind that's kind of like going like this, and I take something and I try to push it along this path. Some of the path I'm getting help, some of the path doesn't care about me, and some of the path it's actually working directly against me. Yes? What I want to do is I want to just pay attention to the stuff where I'm actually either directly opposed, and not my total motion, but my components of my motion. So the parts of my motion that are directly in the same direction, they're getting helped. The parts of my motion that are against the direction of that flow is getting harmed. Yes, I'm getting pushed back. Okay. So not surprisingly, what's going to show up here is an old friend, this guy. Do you guys remember who this guy is? Yeah, in fact, even better, it's the unit tangent vector. Tangent vector was just r prime, and of course t is r prime divided by the length of r prime. I think it's a really good choice of variable for that guy. That's the big ass t, that's the unit tangent vector, he's cool. So what I want to do is, I want to take my force and I want to dot it with the tangent vector of my motion. Because if my motion is perpendicular to the force, it's neither helping nor hurting me. I'm not going to add it into my accumulation. If it's helping me, I'm going to add it. If it's hurting me, I'm going to subtract it. That's why this is a dot line. Kind of wraps in the angle at which this is happening. If I do what I just said, and I parameterize this, and for some reason, oh good, I only did in that one place, so I'll change it. I chose some other weird way to write this. I'm going to write what t was, what I just said. It's the absolute, it's the slope, it's the divided by its length. And then ds, this is something I don't, yeah, okay. I did say this. Let's see if you guys remember. ds was the square root of blah, 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 right? X prime squared plus y. And that's just the length of r prime. Yes? T is r prime divided by its length to make it a unit vector. ds is r prime of t dt. That's where we get the square root of x prime plus y prime plus z prime squared, all of it, yes? What immediately happens there? Those go away, which is always nice to see. So I'm very sorry, I should have said this earlier. This is a derivation of a formula we're going to use. So we're trying to make this look as good as we can make it look, because we're going to use it over and over and over again. And unfortunately for everybody, that's as good as it could look. Well, I should have put a little curve there because it depends on the path I'm taking through the wind or through the electric field or through the magnetic field or whatever it may be. Okay. what we have, let me write this a little bit more succinctly. What we have here, for the first time, the type of integral we were doing earlier is called a scalar line integral, and this is a vector line integral. This is now in a force field. So again, the force field could just be as simple as wind. And if I'm trying to make something move through the wind, bless you, it could either be pushed, it could either be helped the motion I'm trying to go, or it could be hurt the motion I'm trying to go by the wind. So what this does is it collects all the hurts and the helps. It tells you at the end, did you overall get helped more or hurt more as you went through this field? So I have a field that's set up somewhere. I come in out of nowhere with my charge or whatever, and I'm trying to move it through there, and I'm like, how much is the field helping me as I move along this path? How much is it hurting me? That's the basic idea of a line integral across a vector field along a path. Oh my God, Jeff, can you give me an example of that? I don't know. Did I give it? Yes, I did. Yay. Oh my God, I got no time. Yeah, let me talk about this right now. Let me give you this because I want to. I got so much. First, I'm going to give you this. And we haven't talked about everything on here, but I definitely want you to get this today. Give me one more back there for Joel. So this is me collecting notes from the various sections of chapter 16. I lost count. Let's see what happens. Can't do two things at once, are you kidding me? And then this is a little worksheet that we're not going to be able to finish today, but I want to point out a few things on it. Huh? One more? Okay. This is the new one, guys. If I leave you out this time, you can take it personal. I think I did. Okay. Okay.
Was the workforce mass 6.3?
Say again?
Was that the workforce?
Yeah, the force field line integrals are 16.3. Yes. Anytime. All right, so what I want to point out real quick, I want to try to develop this idea intuitively a little bit. Look on the back of this practice sheet that I gave you. You've got this beautiful vector field. So we talked about vector fields in 16.1. We took a break from them in 16.2 to set up an idea of a line integral on its own. 16.3 brings both ideas together. Can you, let me see. Everybody draw anywhere where there's arrows. Draw a closed loop. It doesn't have to be circular. Draw a little closed loop. So I'll do an example. You don't put it exactly where I put mine. I'm going to draw that guy. Little duck. Okay, so already got, you can draw a little circle if you want to, make it easy. You can draw this amorphous blob. You can draw something with more perimeter than area to it because it just turns so much. I don't know why you'd want to do that. So take your, identify a little place. I'm going to start in my duck's, I was going to say nose. They do have nostrils, I think, up on the top of their bill, but let's not talk about duck biology, Jeff. Okay. If I move along my curve, I'm going to choose to go this way. Do you see how for me, it's going to be different for everybody, but for me, is this field I'm living in helping me at first? Along this part, I almost don't care about it, do I? It's not helping or hurting almost, right? Just a little bit helping because I'm sort of at a slope. You with me? So as I move along, so far I've accumulated just about nothing but help, yes? Either doesn't care or help. The minute I start to turn this way, what happens? Now I'm going against. So everything I gained is basically lost. Now, I'm not going to sit here and try to actually measure the arrows and go around and actually get a number. Can you look at your own circle or whatever blob-looking dude you drew? Can you think about it the same way I just did? Can you see how you should get 0 at the end? If you go around your curve, you will get a total of 0 contribution, 0 help, if you want to think of it that way. Like the hurt I would subtract and the help I would add. So I end up with 0. Yes?
Is that only because this is a regular force?
This is a specific type of force field. Vector field, let's say, more general. This vector field is what's called conservative. Every conservative vector field is the gradient of some scalar function. Holy shit, Jeff. Do that again. Every conservative vector field is the gradient of some scalar function. Meaning f is equal to the gradients of some f. What's the gradient do again? We'll say 2 dimensions. So if I give you a function, x squared y, let's see, here.
It's a vector with fx and fy.
Yeah, if I give you f as x squared y, what's the gradient do? What type of answer do I get? Do I get matrix? Do I get, yeah, I get a vector. Jacob's like, let me just cut this guy off. What's the first part? How do I get the first part? df dx, yeah, fx. It's got the movies. And then how do we get the second part? dy, which is x squared. If I plot this, I will get a vector field in which, if you draw any closed loop, it will add up to 0. So knowing something is a conservative vector field kicks a lot of ass. Now the reason that happens is, this is a little more esoteric. This is harder to see. If I pick any starting point and any ending point, it does not matter how I connect the two, I will always get the exact same answer at the end. Sorry, you didn't see what I was just drawing. So if I connect these 2 points in any way I want to, since this is a conservative vector field, I will end up at the end, this is true, with the same exact answer. The only way you can be guaranteed to be path independent is if you're going through a conservative vector field. Dude, that is a phrase that would have made no sense at all if I would have said that first thing today.
So if you can prove that the vector field is conservative,
We have a shortcut as to how to do work with, or how to do some calculus to it. It leads to beautiful shortcuts, which I don't know if I have enough time to get into. Let's do this. Real quick. I think this will be fine. We'll do this first part. We'll finish this up next time. Don't say anything. I think we've done enough that you guys know the answer to 1A. But take a look at C1. Do you think it would come out positive, negative, or 0? What do you think? Why positive? Mostly, the vector field's helping me move, right? If that's me trying to move. Here, it doesn't seem to be bothering me at all, but then as I move along, part of the vector field lines up with where I want to go. So it makes that motion easier. And of course, what about C2? So negative. Now, if this is wind, I am going directly against the wind. Against the wind. Okay, Jeff, show. So this will be positive, this will be negative. Is this field conservative? How can you very quickly tell that it ain't? It ain't conservative.
Stands are zero.
Huh?
I mean,
No, are those closed loops?
No.
No, okay, so good. It has to be closed loops for a conservative vector field's answer to be 0. It has to not care about the path I take, but there's a very quick, can you draw a really simple closed loop that totally has a positive answer?
Yeah.
Because the freaking field itself is circular, right? So if I draw this closed loop, yes? And they go this way, will the answer be 0? Nope, so it's not conservative. Is it possible you can find a vector field and find a little piece of it that you can draw a circle and it comes out 0?
Yeah.
Hell yeah, hell yeah. Does that mean shit about it generally? Hell no. So of course some functions are going to have little non-eddies. An eddy would actually lead to not a 0 answer. Does that make sense? Eddies are like things that have certain... So it could have a little piece of itself that if you drew a circle in it, it comes out to be 0. But who cares? The whole thing has to be true. Nowhere should change. Everywhere you put a circle loop in a conservative vector field, it'll come out to be 0. Okay. No. This is why. Okay. And here is where I think we'll pick up next time. I'm going to let you guys out. This is just practicing setting up parameterizations of different curves. And just to point this out, the other sheet I gave you, this guy, so here's scalar line integrals, vector field integrals. We didn't quite get here, but this is what conservative vector fields do for me. It makes integration much easier. I just need the endpoints then. If I'm path independent, I could just take the endpoints and see. So we'll get there. All right, guys, that's enough. Oh my God. So Monday we have a quiz, not next time. Okay. I'm saying that for future me.